This is Physics 221, Mathematical Physics 1, and in this lesson, we're going to discuss about vector calculus. Let us consider a vector A that is a function of a scalar variable u. By this we mean that with each value of u, we associate a vector AU, and that vector AU, we write it as your AU is equal to AXI plus AYJ plus AZK. And just remember that if we're going to have this one handwritten, write this one as your vector AU AXI hat plus your AYJ hat plus your AZK hat. This is just in reference. For example, if you see other ways of writing this vector here. Now, in Cartesian coordinates, the derivative of vector A is the derivative of vector A with respect to u is your dA over du, and that is equal to the derivative of dAx du I plus dAy du j plus dAz du k. Or if we have this one handwritten, this is your dA over du dAx over du I hat plus dAy over du j hat plus dAz over du k hat. So this is the derivative of a vector AU with respect to your scalar variable u. For example, in classical mechanics, if the time-dependent position vector of the particle with respect to the region in Cartesian coordinates is given by your vector r of t is equal to x of ti plus y of tj plus z of tk, then the velocity of the particle is given by the derivative of this function here, and that is your velocity p of t is equal to the time derivative of dr over dt, and this is equal to your dx over dt I plus dy over dt j plus dz over dt k. And you have here your dx over dt. This is your dx, okay, your x component of your velocity, and then here this is your vy, the y component of your velocity, and then this is your vz, the z component of your velocity. So we can write now then your velocity of the particle by the vector v of t, and this is vx I hat plus vy j hat plus vz k hat. Okay, and just again, the velocity of the particle is given by the first derivative of your vector r of t. The acceleration of the particle is given in a similar manner, and your acceleration is just the time derivative of your velocity function v of t. So that is equal to your dv over dt, and this is equal to the second time derivative of your time-dependent position vector. So that is equal to your d squared x over dt squared I plus dy squared over dt squared j plus t squared z over dt squared k. So as you see, it's the second time derivative of your time-dependent position vector of the particle, but it's just the first derivative of your velocity vector. So your a of t, your vector a of t, is just your dv over dt. If we use this term here, so you have the derivative of your dvx over dt plus your dvy over dt. You have here your I hat, have here your j hat, plus your dvz over dt k hat. and you go back upwards. So that makes it your acceleration is the second time derivative of your time dependent position vector. So this is a classic example of your differentiation of vector in application to your classical mechanics. Now let us have an example. The position vector of a particle at time t in Cartesian coordinates is given by r of t equal to 2t squared I plus 3t minus 2j plus 3t squared minus 1k. Find the speed of the particle at time equals 1 and the component of its acceleration in the direction s is equal to I plus 2j plus k. So again, find the position vector of a particle at time t in Cartesian coordinates is given by r of t equal to 2t squared I plus 3t minus 2j plus 3t squared minus 1k. Find the speed of the particle at time equals 1 and the component of its acceleration in the direction s is equal to I plus 2j plus k. So in this problem, we are asked of two targets. First is the speed of the particle at time equals 1, and next the component of its acceleration in the direction of s, of your vector s. So you have here your position vector r of t. You have 2t squared I. So let me write it that way. Plus 3t minus 2j hat plus 3t squared minus 1k hat. Remember here that this is your x component, your y component, and then your z component. And first, we're asked to find for the speed of the particle at time equals 1. And again, your v of t is equal to your dx over dt I hat plus dy over dt j hat plus dz over dt a hat. So we're going to take the derivative of these components, your x component, your y component, and then your z component in this velocity vector here. Okay, so the velocity of the particle is just your dr over dt. So the derivative of dx over dt. So your 2t squared is equal to, so again here, the derivative of this one, your x component with respect to t, is you have your uh, 2 times 2 t, so that is 4ti, and the derivative of this one, since 2 is a constant, so it just it goes to 0, and then for 3t, so you have 3. The derivative of 3t is 3, so you have 3j, and then for this one, you have 2 times 3t minus 0 times k, so the derivative is 60k. So this is the velocity of the particle, and we're asked of uh, the speed of the particle at time equals 1, which we'll just find later. So let's proceed first to the acceleration vector. So the acceleration is just the time derivative of this one, of your 40i plus 3j plus 60k. So the acceleration of the particle, your dv over dt, is equal to, first you take your dvx over dt plus your dvy over dt, and then your dvz over dt. You have your hats, your directions, your unit vectors. So this is your dv over dt. Okay, so the derivative of the first, your x component, is just 4. So you have 4i. This is just a constant, so this is 0. So you don't have a component on the y-axis. And for your 6tk, the derivative of this one with respect to t is just 6. So the acceleration of the particle, dv over dt, is equal to 4i plus 6k, or your 4i hat plus 6k hat. Now let's find the speed of the particle at time equals 1. So the speed of the particle is given by the component of this one, okay? Or sorry, the magnitude of this one. And you can get it by um, taking the time derivative, taking the, what do you call this? You take the from your Pythagorean theorem. If the speed of the particle at t equals 1 is simply the magnitude of v of t, again, because we are asked here of the speed, okay? So when you're asked of the speed, you take the magnitude of your vector. So the magnitude of your vector, you take it from the square root of the sum of the squares, or just from your Pythagorean theorem. So your speed at time equals 1 is equal to the square root of uh, 4 times 1 squared plus 3 plus 6 squared. So that is equal to square root of 61. So to show it, so let's just write the solution. What we first do is um, remember that you have here your d of t. So you have 4t I hat plus 3j plus 6t k hat. So all of the t, we are going to replace it with t is equal to 1. So you have 4, 1 I hat plus 3 j hat plus 6 times 1 k hat. So you have 4 I hat plus 3j hat plus 6k hat. And since you're asked of the speed, so we get the magnitude of this vector here. And the magnitude is equal to the square root of 4 squared plus 3 squared plus 6 squared. And the magnitude is equal to square root of 61. So that is the speed of the particle at time equals 1. And let me just erase this one. Next, let's find the component of its acceleration in the direction of your s. And when we're talking about in the direction of s, remember that your vector s, this is equal to the magnitude of s times your unit vector s hat. And we're asked here of the component of its acceleration in the direction of s. So when we say about in the direction of s, what we mean by your s hat, which is equal to your vector s divided by the magnitude of s. And we're asked here of the component of its acceleration in the direction of s, meaning we are asked of the dot product, okay? The dot product of your vector A with your uh, s hat. Okay, so to solve that one, the component of the particle in the direction of s is equal to your vector A dot with your s hat. So you have first your vector A here for I plus 6k dot with your I plus 2j plus k, your s hat, divided by the magnitude of your s hat. So you have, from your Pythagorean theorem again, you have 1 square root of 1 squared plus 2 squared plus 1. And we get an answer of equal to 5 times the square root of 6 divided by 3. So this is the component of the particle in the direction of s. So again, we did the dot product because we are asked of the component of the particle in the direction of s. That is, we are going to project your acceleration vector in the direction of your s vector. Now let's talk about the differentiation of composite vector expressions. So this is the case when you have a composite vector expression and then you want to take the derivative of this composite expression. Assume that vector A and vector B are differentiable vector functions of a scalar u and that phi is a differentiable scalar function of u. And if you have this kind of composite expressions, you have your phi times your A, and you want to take the derivative of this one. Again, your phi is a differentiable scalar function of u. So this is just a scalar function, your phi. And we take the derivative of this one respect to u. So you have your over du of phi times a. So the derivative of this one is just phi times dA over du. So the derivative of your vector plus d phi over du, the derivative of your scalar function, times a. So this is the derivative of your phi times a. If instead you have the dot product of a and b, and then we take the derivative of this one with respect to u, so you have d over du of a dot b, so that is just a dot the derivative of b with respect to u plus the derivative of a with respect to u dot b. So it's a dot dv over du plus dA over du dot b. Lastly, if we have um, the cross product of a and b, so the derivative of a cross b with respect to u is equal to your a cross db over du plus dA over du cross b. So it's a cross db over du plus dA over du cross b. So these are your derivatives for your composite functions. Just um, your phi and a, where phi is a scalar function, and then you have your a dot b, and then you have your a cross b. So let's have an example. A particle of mass m with position vector r relative to some origin O experiences a force F, which produces a torque, or the moment, which is equal to your torque is equal to your R cross your F, about your origin. The angular momentum of the particle about the origin is given by your L is equal to your R cross your mv, where your v is the particle's velocity. Again, a particle of mass m with position vector r relative to some origin O experiences a force F, which produces a torque, or we also call your torque as your moment. E is equal to r cross your F. So your vector t is equal to your vector r cross your vector F about the origin. The angular momentum of the particle about the origin is given by your L is equal to r cross mv, where v is the particle's velocity. Show that the rate of change of angular momentum is equal to the applied torque. So we are asked to show that the rate of the angular momentum is equal to the applied torque. That is, we're asked to show if um, rate of change of your angular momentum, you have dl over dt is equal to the applied torque. So that's equal to t. Okay, so the rate of change of your angular momentum is given by this function. So you have your dl over dt is equal to the time derivative of your r cross your mv. So this is again your angular momentum. So we're going to take the time derivative of this one, your dt over d over dt of r cross mv. And remember from our previous slide that the derivative of your a cross b is equal to this one. So you take first your first vector, cross it with the derivative of your second vector, plus your dA over du cross your b, your second vector. So we'll apply this one to this function here, okay? And you see that first you have your uh, you can just actually interchange it. So you have your dr over dt cross mb plus your r cross d over dt mb. So we actually just interchange here these two components, and this is your dl over dt, and your dr over dt, this is just the velocity. You can remember this is just your velocity, and then cross it with your mb plus your r cross your d over dt of your mb. Okay, and remember that your mv, the time derivative of your b, is the acceleration. Okay, so Just remember that since m is a constant, we can take m outside of your derivative. So you have v, dv over dt. And this is just equal to your acceleration. And your m times your acceleration is equal to some force F. Okay, so your b cross mb, since your b, your velocity v cross your velocity b points in the same direction, the cross product of this one is equal to 0. Okay, and you have now you are left with r cross your f here. Okay, your r cross your f is just given by your torque. So that means you're able to show that your dl over dt is equal to your torque. For the integration of a vector or of an expression involving vectors that may itself be either a vector or a scalar, with respect to a scalar u, can be regarded as the inverse of differentiation. We must remember, however, that the integral has the same nature, either vector or scalar, as the integrand, and the concept of integration for indefinite integrals must be of the same nature as the integral. When we're talking about your derivatives, so it always follows that you have your integrals. So let's talk about the integration of your vectors. For example, if AU, your vector AU is equal to dAU over du. Okay, so let's just write it again. So if you have your vector A of u, and then this is equal to your dA of u over du, then the indefinite integral of your AU is given by the integral of AU times du, which is equal to your AU plus B. So what we did here is we want to evaluate this. We want to get AU. So we multiplied AU with your du. So on the right hand side, you have your dA of u over or just your dA of u. And we evaluated this one. We take the integral both sides. Okay, so the integral of AU times du is equal to your AU plus some constant b, where b is a constant vector. The definite integral of AU from u is equal to 1 to u is equal to u2 is given by the integral of AU du evaluated from u1 to u2. That is equal to a times u2 minus a times u1. So this just follows your um, integration as you have learned in your calculus. Now let's talk about your scalar and your vector fields. So in this section, we turn to the case where a particular scalar or vector quantity is defined not just as a point in space, but continuously as a field throughout some region of space R, which is often the whole space. So previously, when we are talking about your scalar and then your vector quantities, what we meant are just your quantities which are represented by a point in space. This time, you're going to extend your scalar and then your vector quantities as scalar and vector fields, which is a field throughout some region of space R. Let's say, for example, you have this one here. You have this your vector field here. The field concept is valid for spaces with arbitrary number of dimensions, but in this lesson, we just restrict our attention to the familiar three-dimensional case. So you have your x, y, and z axis. So let's talk first about your scalar field. The scalar field, represented by your phi of xyz, associates a scalar with each point in R, your space R. This is a function that gives us a single value of some variable for every point in space. And examples of your scalar field, we have the pressure at each point in a fluid, your electrostatic potential V at each point in space in the presence of an electric charge. What we have here is, as an example, is the nighttime temperature map for Mars. And the various colors in the map represent the surface temperature, which is a scalar quantity. This map, however, is limited to representing only the temperature. So you see, uh, uh, the color of your vector quantity here, or your vector field, represents how hot or how cold your temperature is in the surface of your Mars. Okay, so your scalar field, this is again a quantity that associates a scalar, or it's not a quantity, it's a field that associates a scalar with each point in the space R. On the other hand, your vector field, represented by your vector A, x, y, z, associates a vector with each point in R in the space R. Common examples of this one are your velocity vector in a fluid and then your electric field. What you have here in the figure is your electric field lines for two charges, and this is just a simulation of your electric field lines with increasing density of your electric field lines. So your electric field lines are vector quantities. So it associates a vector, your vector field, with each point in the space R. So certain differential operations may be performed on scalar and vector fields and have wide-ranging applications in the physical science. And I guess the most important vector operator or vector operations are those of finding the gradient of a scalar field and then the divergence and the curl of a vector field. It is usual to define these operations from a strictly mathematical point of view, as we'll do here. So in this section, we will discuss the geometrical definitions, which rely on the concept of integrating vector quantities along lines and over surfaces. And central to all differential operations is the vector operator del. So you have here your inverted triangle, which is called the del, or sometimes the nabla. So in Cartesian coordinates, your del or your nabla is given by um, your I, your I hat, your partial derivative, your partial x, partial x plus your j partial y plus your k partial z. So this form, the form of this operator in non-Cartesian coordinate will be discussed in the next lesson. So just remember this one. This is your del operator, or your sometimes also called your nabla. So let's talk about the first application of your del operator, which is on the gradient of a scalar field. The gradient of a scalar field represented by your phi xyz is defined as your gradient of phi, your gradient phi, that is equal to your del phi, and is equal to your I partial phi over partial x plus j partial phi over partial y plus k partial phi over partial z. Here, as you can see, your scalar field phi becomes a vector field. So your del phi is a vector field whose x, y, and z components are the first partial derivatives of your phi of x, y, z with respect to x, y, and z respectively. So this is the x component of your vector field, your y component, and then your z component. So again, after you apply your del operator to your scalar field phi, your scalar field becomes a vector field del phi. So let's have an example. Find the gradient of the scalar field phi that is equal to xy squared z cubed. So here, we're asked to find for the gradient of this scalar field phi here. Just remember that your scalar field, or your gradient of your scalar field, del phi, is equal to the first partial derivative of your function. So we have partial x of xy squared z cubed I hat plus partial y of xy squared z cubed. Then this is j hat plus partial over partial z of xy squared z cubed. And then this is k hat. So what we just do is take the partial derivative with respect to x of your function first, and then with respect to y, and then with respect to z. So for the partial derivative with respect to x, so we have y squared z cubed I hat. Next, with respect to y, plus, so you have 2x y z cubed j hat. And then we take the partial derivative with respect to z. So you have x y squared 3 c squared k hat. So this is the gradient of your scalar field phi xy squared xy squared z cubed. So we have your gradient of your scalar field. Next, we have your divergence of your vector field. The divergence of a vector field of your vector field A, x, y, z is defined as the divergence of A, which is equal to your del dot A, and this is equal to the partial derivative with respect to x of ax plus the partial derivative of ay with respect to y, and then the partial derivative of az with respect to z, where ax, ay, and az are the x and y components of your vector A. Here, as you can see, since this is a dot product of your del operator and then your vector A, del dot A is a scalar field. And any vector A for which your del dot A is equal to 0 is called a solenoidal. So again, let's just review your divergence of your vector field, which is your del dot A for a vector field A is equal to your partial x of ax plus partial y of ay plus partial z of az. Let's have an example. Find the divergence of the vector field A given by x squared y squared I plus y squared z squared j plus x squared z squared k. So we're asked of the divergence of this vector field here. And let's just label these components. So you have here your ax, and then this is your ay, and then here this is your az. And just remember that the divergence of your vector field A is just your del dot A, which is equal to the partial derivative with respect to x of your ax plus the partial derivative with respect to y of your ay plus the partial derivative with respect to z of your az. So again, this is your x component, your y component, and then your z component. So we take the partial derivative of your ax, which is x squared y squared plus the partial derivative with respect to y of y squared z squared plus the partial derivative with respect to z of x squared z squared. So here, the partial derivative is equal to 2xy squared plus, you have here 2y z squared plus, you have 2x squared z. Or we can take your number 2 outside. So you have 2 times xy squared plus yz squared plus x squared z. So this is the divergence of your vector field given in the problem. The divergence can be considered as a quantitative measure of how much a vector field diverges or spreads out or converges at any given point. So this is how you illustrate the divergence, the spread out, and the convergence. Okay, this is the case for when your divergence is greater than 0 or is a positive, so it spreads out. And this one is for when your divergence is negative, so it um, it converges, and this is when your divergence is equal to 0. We will discuss fully the geometric definition of divergence and its physical meaning in the next lesson. If some vector A is itself derived from scalar field by your vector field A is equal to your del phi, then your del A has the form of del dot del phi, or as usually written as your del squared phi, where your del squared is the scalar differential operator. Del squared is equal to the second partial derivative with respect to x, y, and z. So again, uh, if your vector A is equal to your del phi, okay, and we take the del of A, we take the del dot A, then this is equal to your del dot your del phi, okay, or this is your del squared phi. Okay, your del squared phi is called the Laplacian of phi, and it appears in several important partial differential equations of mathematical physics. So it's the Laplacian operator of phi. Let's have an example. Find the Laplacian of the scalar field phi, where phi is equal to xy squared z cubed. So let's find for the Laplacian of the scalar field. So again, your Laplacian of phi or your del squared phi is equal to uh, the second partial derivative of your function. So you have this one here, or as I like to write it, I usually do it with your partial x, and then partial x p plus your partial y, your partial y phi plus your partial z, partial z phi. Okay. So then let's take the first partial derivative of your function with respect to x. So it's equal to y squared z cubed. And next, the first partial derivative with respect to y is 2xy z cubed. And next, the first partial derivative with respect to z is 3xy squared z squared. Then we take the second partial derivative. So the second partial derivative of this one is 0. So this is 0 plus you have 2xz cubed plus you have 3 uh, times 2 xy squared z. Or you have this answer. So you have 2x cubed plus 6xy squared z. So we already now have the gradient, and then next we have the divergence. Now let's talk about the curl of a field. The curl of a vector field given by your vector field A, x, y, z is defined as your curl A is equal to your del cross A. Okay, and this is your del cross A. You have your partial AZ over partial Y minus partial AY over partial Z I plus you have your partial AX over partial Z minus partial AZ over partial X J plus your partial AY over your partial X minus your partial AX over partial Y K. Where here your AX, AY, and AZ are the X and Y components of your vector A. The right-hand side can be written in a more memorable form as in the determinant here, because this is a little bit harder to remember. So we can write your the right-hand side of your equation in the determinant form, where here your del cross A, your curl of your vector A, is equal to the determinant here, where above you have your unit vectors I, j, k, and then it's followed by your del operator components. So you have your partial over partial x, partial over partial y, and then partial over partial z, and then your ax, ay, and az. So you just evaluate this determinant here, okay, just like how we did in the previous lectures. So here, your del cross A is itself a vector quantity, and any vector field A for which your del cross A is equal to 0 is called irrotational. The curl of a vector field is formally defined as the circulation density at each point of the field. And we're going to talk more about the geometric definition of your curl and its physical meaning in the next lesson. So let's have an example. Find the curl of the vector field A. You have your x squared y squared z squared I plus y squared z squared j plus x squared z squared k. Okay, so we're asked to find for the vector field of this, or the curl of this vector field A here. Now, the curl of your vector field is just your del cross your A, which is equal to this one. So we write it in terms of the determinant, but you can also use the formula earlier. So on top of your determinant are your unit vectors, your I hat, your j hat, and then your k hat. And then next, the components of your del operator, your partial over partial x, partial y, and then partial z. And next, you have your x, y, and z components of your vector field A. So you just, I'll give it to you to solve this problem. You just evaluate the matrix to find for the determinant, and you are supposed to get this answer. So I hope you evaluate this determinant yourself to verify that it is indeed your the answer to the curl of your vector field A. So please solve this one on your own. You may pause the video for a while. Lastly, let's talk about the vector operators acting on sums and products. Here we let phi and your psi be uh, here we let your again your phi and then your psi be scalar fields, and a and b be vector fields. Assuming that these fields are differentiable, the action of gradient, divergence, and curl on various sums and products are given by the following. So for the sum of your scalar fields phi and psi, you have your divergence. It's just your del phi plus del psi. For the divergence, sorry, the earlier is gradient, and for the divergence of your vector fields A and B, it's the del dot A plus the del dot B, and for the curl of your A plus B, it's del cross A plus B, so it's del cross A plus del cross B. And for the product of your scalar fields, your del phi psi, it's phi del psi plus psi del phi. And for del of the dot product of A and B, it's given by this one here. And for the divergence of your P and the P times A is your phi del dot A plus A dot del phi. And for the del of the dot the del dot of your cross product of A and B, it's this one here. And for your del cross PA, it's del phi cross A plus phi del cross A. And for del cross A cross B, it's this one here. So these are some of the vector operators acting on the sums and the products.